All right, so let's review what we've learned about functions in the first 9 lessons. I'm going to give you guys some practice problems. So as usual, I want you to pause the video, work out these problems, and then we'll go over the solutions. All right, so on the first one, we have this relation, x equals y squared. I want to find 2 points on the graph of that relation that if you took those 2 points, it would prove that that relation is not a function. So remember, if your relation is not a function, then it's going to fail the vertical line test. So we want to find 2 points that cause this graph to fail the vertical line test. So maybe we should make a graph of it. Whether I tell you to make a graph or not, it's always a good idea to make a graph so that you can see what's going on. So let's plot some points. Okay, so we have x is on horizontal axis, y is on the vertical axis. All right, so let's plug some things in. If I put in a 0 for my x, then y would have to be 0. 0 squared is 0, so I know I have that point. Let's put in a 1 for the x. So if I put in a 1 for x, what will y have to be? Okay, so what number squared would give me 1? Well, 1 squared is 1. But negative 1 squared is also 1. So if x is 1, y could be 1 or negative 1. All right. What if I plugged in maybe a 4 for my x? So 1, 2, 3, 4. So if I plug in 4 for x, what does y have to be? Well, y could be 2, because 2 squared is 4. Or y could be negative 2, because negative 2 squared is 4. What if I plugged in 8, 9? What if I plugged in a 9 for my x? So if x is 9, what does y have to be? Well, y could be 3, because 3 squared is 9. But y could also be negative 3, because negative 3 squared is 9. So we see that we get this sideways parabola. And clearly that fails the vertical line test at an infinite number of points. Let's just take this point. This is a nice one. Fails the vertical line test there. What 2 points show that it fails the vertical line test? Well, we have the point 9, 3. And we also have the point 9, negative 3. So these 2 points show that that's not a function. I have the same x, but I have different y values. And of course, there's an infinite number of answers you could have come up with. You could have used 4, 2 and 4, negative 2, or you could have used 1, 1 and 1, negative 1, or anything in between, or anything on out that way. All right, let's have a look at the second question. What numbers are not in the domain of this function? So remember, the domain is all the x values that you're allowed to plug into the function, the ones that work. So a couple of ways that you guys know right now that functions can go wrong is, number 1, you having a 0 on the bottom of the fraction. You're not allowed to have a 0 in the denominator. Okay, so that's one thing that can go wrong. A second thing is having a negative number underneath the square root. For now, we're dealing with real numbers, so we can't take the square root of a negative number. So those 2 things are things you need to look for that go wrong in the domain of a function. All right, so let's take care of the bottom one. What value of x would cause this denominator to be 0? Okay, so let's just answer that question. 5 times x plus 7 squared minus 45. I want to know what value of x will cause this to equal 0, because having 0 in the denominator is a bad thing. All right, so let's solve this quadratic equation. I'm going to add 45 to both sides. squared. Then I'm going to divide both sides by 5. And get 9. I'm going to take the square root of both sides. Remember, I got two solutions. Plus or minus the square root of 9 is plus or minus 3. I subtract 7 from both sides. So negative 7 plus 3 or negative 7 minus 3. So I have x equals negative 7 plus 3 is negative 4. Negative 7 minus 3 is negative 10. So I'm claiming that negative 4 and negative 10 cannot be in the denominator, cannot be in the domain of that function. Okay, so let's check what happens. If I put negative 4 into this function for x, negative 4 plus 7 is 3. 3 squared is 9. 5 times 9 is 45. 45 minus 45 gives me a 0 in the denominator. So negative 4 cannot be in the domain. Let's check negative 10. Negative 10 plus 7 is negative 3. Negative 3 squared is 9. 5 times 9 is 45. 45 minus 45 is 0. Negative 10 will cause me to have a 0 in the denominator. So negative 4 and negative 10 are not in the domain of that function. All right. We're not allowed to have negative numbers underneath the square root. So I would also like to know, when is 2x plus 26 less than 0? Okay, so any number that satisfies that inequality is not in the domain. So I'm going to subtract 26 from both sides. Divide both sides by 2. I'm dividing by a positive number, so I do not have to change the way that inequality points. Now, I just said do not, and then I changed it. It stays the same because I'm dividing by a positive number. So that'll be negative 13. All right, so any number less than negative 13 is not in the domain. For instance, if I put negative 14 in for x, 2 times negative 14 is negative 28. Negative 28 plus 26 is negative 2. And the square root of negative 2 is not a real number. So we're going to say that's not in the domain of this function. All right, let's graph on a number line the numbers that are not in the domain. All right, so I have negative 13, negative 10, and negative 4. All right, so I'm going to graph all the numbers not in the domain. So negative 4, not in the domain. Negative 10 is not in the domain. Anything less than negative 13 is not in the domain. So open circle, and anything this way. Okay, so if I pick negative 4, negative 10, or anything less than negative 13, this function will not be defined, where it will not be real. So none of those numbers are in the domain. All right, here are two more problems. Again, pause the video, work these out, and then we'll go over the solutions. All right, so what numbers are in the range of this function? So remember, range is the set of numbers that the function spits out. It's the output of the function. Okay? The range is graphed on the vertical axis. Domain is on the horizontal axis. So I want to know the numbers in the range. Okay, again, I don't tell you to make a graph, but if you had a graph of this function, it would be really easy to see what the range is. So maybe we should make a graph. Okay, just because I don't tell you to graph something doesn't mean that you shouldn't graph it. It's always a good idea to graph things so that you can see what's going on. All right, so let's make a graph of this function. All right, I know what the function x squared looks like. Y equals x squared. That's just a parabola. The vertex is the origin. Since we've studied transformations of functions, I know what the 3, the 7, and the negative 5 will do to that basic parabola. I know that the plus 3 inside the parentheses will shift it 3 to the left. I know the negative 5 will flip it upside down, make it skinnier. And I know that the plus 7 will shift it up 7. So let's make a graph of that. So the original y equals x squared parabola is the vertex is at the origin. It looks like that. So if I shift that left 3, a little bigger. 1, 2, 3. I'm going to go left 3. -5 will flip it upside down. So it looks like this. Flip it upside down. Now it looks like that. The 5 will make it a little skinnier, as you saw, so it's going to look more like this. And the +7 will shift it up 7. 1, 2, 3, 4, 5, 6, 7. Okay, so my vertex got shifted left 3 and up 7. So here's my vertex. And now the parabola is upside down. So it looks like that. And now it's really easy to see what the range is. The parabola keeps going down this way forever. So my range, so I'm looking at the y-axis, my range is from -infinity all the way up to 7. So the range is from -infinity all the way to 7. Infinities always have the open parenthesis on them. Okay, the 7 is included in the range, so I'm going to use a square bracket. So there's my range. My range is from -infinity all the way up to 7, including the 7. So if I put that on a number line, I would have 7 included. And it would be all the numbers from -infinity to 7. All right, let's look at the next question. So I've given you a function. I want the initial value. Remember that the initial value is the y-intercept, or it's f of 0. So if I plug 0 into this function, and for x, I'll get the y-intercept. That's the initial value. So f of 0, I'm going to put a 0 here. I have -4 times 0 minus 5 squared plus 7. All right, 0 minus 5 is -5. -5 squared is 25. -4 times 25 is -100. -100 plus 7 is -93. All right, find the roots of f. Remember, roots is another word for zeros. And so zeros and roots mean the same thing. Initial value was the y-intercept. Your roots, or your zeros, are the x-intercepts. Okay, so I want to find the x-intercepts of this function. In order to find the x-intercepts, I plug 0 in for y. So I'm going to say 0 equals -4 times x minus 5 squared plus 7. And then that's an easy quadratic equation to solve. I'm going to subtract 7 from both sides. I'm going to divide both sides by -4. -7 divided by -4 is positive 7 over 4. Take the square root of both sides. Remember, I get 2 solutions. So x minus 5 equals plus or minus the square root of 7 over 4. I'm going to add 5 to both sides. So I will have x equals 5 plus or minus the square root of 7 over 4. That's a good answer. I'm going to clean it up a little. Remember that square root of a fraction, I can do the square root of the top over the square root of the bottom. So the square root of 7 on the top and the square root of 4 on the bottom, square root of 4 is 2. So I can write it like that. Make sure you understand here the square root is covering up the entire fraction. 7 over 4 is underneath the radical. Here, only the 7 is underneath the radical. The square root is only covering up the 7. The 2 is on the bottom by itself. All right, 2 more problems for you. Again, pause the video, work these out, and then we'll go over the solutions. All right, so number 5. So I have the function g of x equals the absolute value of x. I want 2 points that, if you took those 2 points, would show that this function is not 1 to 1. So remember, 1 to 1 is the horizontal line test. Okay, so we want a function that fails the horizontal line test. So it'll not be 1 to 1. So we need to find 2 points that I can draw 2 points on the graph that I can draw a horizontal line through. All right, so let's make a graph of this. So x, g of x. All right, if I plug 0 into this function, I get 0. If I plug in a 1, I get a 1. If I plug in a 2, I get 2. If I plug in 3, I get 3, and so on. So it'll look like this. If I plug in -1, absolute value of -1 is 1. Absolute value of -2 is 2. Absolute value of -3 is 3. And we get that. All right, so now all I need is 2 points that show that this fails the horizontal line test. So these 2 right here look nice. So this point is 3, 3. This point is -3, 3. And these 2 points show that this function is not 1 to 1. I've got the same y, but 2 different x's. I plot these 2 points, I can draw a horizontal line through it, and it fails the horizontal line test, and hence is not 1 to 1. Of course, you could have used any, or an infinite number of points would be answers. You could use 2, 2, and -2, 2. Or 1, 1, and -1, 1. Any of those would work. All right, so here I've given you the graph of some function f. I want to know on what intervals is f positive, increasing, or concave up. And when I say what intervals, I mean what intervals of x, what x intervals. All right, so where is this function positive? Or where does the function spit out a positive y value? So if I plug in, say, numbers right in here, the function spits out positive numbers. So I'm looking for x values that will cause this function or this graph to be above the x-axis. So this function is above the x-axis from -3 on this way forever. So this thing is positive from -3 to infinity. I can plug in any value bigger than -3, and the function will spit out a positive number. Infinities will always get the open parenthesis. All right, do we want to include the -3 or not? If I plug -3 into this function, I get a 0. 0 is not positive or negative. It's neither positive nor negative. So -3 will not cause the function to spit out a positive answer. So we don't want to include it. So we're going to use an open parenthesis. Where is the function increasing? So that means the function is going uphill. If you were a little bug walking from left to right on the function, where would you be going uphill? So if I'm a little bug and I'm going that way, I'm going uphill, 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 uphill until I get to here. Then I'm going downhill, 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 down, down, down until I get to here. And then I'll start going up again. All right, so if I'm this little bug, walked along this function, I'm going to be going uphill from -infinity. So as far out this way as I can go forever. Increasing, 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 all the way to 2. Infinities always get open parentheses. Do I include the 2 or not? So am I going uphill at 2? Well, up here at 2, I'm at the top of the hill. So it's flat up there. I'm not going up or down at that point. Okay. So I don't want to include the 2, because that wouldn't be going uphill or downhill. All right. So I'm increasing from negative infinity to 2. I'm also increasing from 5 on this way forever. So from 5 to infinity. Infinity is always going to open parenthesis. At 5, I'm not increasing or decreasing. I'm at the bottom of a hill, so it's kind of flat down there. So again, I'm going to use an open parenthesis. All right, where is it concave up? Okay, so where does this function open up? Like this. This is opening down. This is opening up. So where does it open up? So it's going to open up here to this point right here. So on all this part of the graph, it's opening up. You see at this inflection point, it kind of switches and starts opening down. Okay, so from here to here, that's opening down. Right here it switches, and then it's opening up. So this is concave up from 4 to infinity. Infinity is always getting open parenthesis. It's not concave up or down at 4. That's where it switches at. That's an inflection point, so we're not going to include that. And we'll use an open parenthesis. All right, so here are 2 more questions. Again, pause the video, work them out, and then we'll go over the solutions. All right, so let's make a graph of this piecewise function. So again, this is just a function where we use 3 different equations. We use this equation if x is less than or equal to 0. We use this equation if x is between 0 and 3, including 3. We use this equation if x is bigger than 3. All right, so if I plug 0 into this function, I will use the top equation because x equals 0. So if I plug 0 in here, I get 3. 1, 2, 3. So we have that point. All right, let's plug in a negative 1. Since negative 1 is less than 0, I'll use this. So if I put in negative 1, I'll get negative 2 plus 3 would be 1. If I put in a negative 2 to the function, I'll use this equation because negative 2 is less than 0. 2 times negative 2 is negative 4. Negative 4 plus 3 is negative 1. I'll get that. And of course, you guys realize this is just a linear equation. That's a line with a y-intercept of 3 and a slope of 2. So it should look like that and go on forever that way. It'll stop when I get to 0 because that's the biggest number I can plug in for x and use that equation. It'll go on this way forever. All right, if I plug in x is between 0 and 3, I'm going to use this equation. So let's plug in 3. So if I put in a 3 to this equation, 2 to the third is 8. 1, 2, 3, 4, 5, 6, 7, 8. If I plug 2 into this equation, 2 is between 0 and 3. 2 squared is 4, which is 4. So that's there. If I plug 1 into this equation, 2 to the first is 2. So that's there. All right. If I plug 0 into this equation, I can't. I'm not allowed to because 0 is not less than 0. It's equal to it. So I'm not really allowed to plug 0 into this equation. But if I did, 2 to the 0 is 1. Remember, anything to the 0 power besides 0 is equal to 1. Okay, so 2 to the 0 is 1. Okay, so if I plug 0 into this equation, I would get a 1. I'm not allowed to, so I'm going to use an open circle. That means that point is not really there. But it means I can plug in numbers as close as I want to 0 and actually get points. So I can plug in numbers like 1/2 or 1/4 or 1/10, and I would get a value up here as close as I want. So the graph of this looks like that, and it'll stop right there at 3. Okay, so again, if I plug 0 into this function, f of 0, I get 3. I get this solid point. I don't get the open circle. But if I plug 0 into this equation, I would get 1, so I'm going to plot it with an open circle. All right, let's graph the square root of x if x is bigger than 3. Okay, so if I were to plug in 4, square root of 4 is 2. So I would get 2. Then 5, 6, 7, 8, 9. If I plug in a 9, I would get a 3. You guys know what the absolute value function or the square root function looks like. Looks like this, on out that way forever. All right. I'm not allowed to plug 3 in here, but if I did, what would the square root of 3 be? Well, I don't know exactly what it is, but I do know that it's between 1 and 2. Because the square root of 4 is 2. The square root of 1, yeah, it's between 1 and 2, right? Square root of 3 is between 1 and 2. So somewhere about right in here, I'm going to have an open circle, and my graph is going to look like that. On out that way forever. All right, so let's have a look at this problem. So t seconds after an experiment begins, the velocity of a particle is given by this function. So when you have a word problem, you always need to understand what all the variables mean. What does t represent, and what does the function spit out? What does v represent? So here, t is measured in seconds. So I plug in the number of seconds after the experiment began for t. So I plug in a time, and this function spits out the velocity of the particle. Okay, so t stands for seconds, or v stands for velocity, which is measured in miles per hour. All right, I want to know the average acceleration of the particle over that time interval. So from t equals 2 to t equals 5. All right, you have to know the definition of acceleration. So the average acceleration is the change in velocity over the change in time. So we should be able to figure that out. To find the change in velocity, I'm going to need the velocity at 5 seconds and the velocity at 2 seconds. So to get the velocity at 5 seconds, I'm going to do the 5. So I'm going to plug 5 into the velocity function. Plug in 5 for t, that'll tell me how fast the particle's going at 5 seconds. I'm going to subtract how fast the particle is going at 2 seconds. That'll tell me the change in velocity over the change in time. So that'll be 5 minus 2. When doing a word problem, you always need to keep the units in there. So up here, velocity is measured in miles per hour. Down here, time is measured in seconds. All right, so now it's just a matter of plugging in numbers. All right, v of 5. So if I plug 5 in here, 5 to the third is 125. 4 times 5 is 20. 125 minus 20 is 105. 105 plus 10 is 115. 115 minus, I plug in a 2. 2 to the third is 8. 4 times 2 is 8. 8 minus 8 is 0. 0 plus 10 is 10. All right, let's double check that because I'm a little worried I didn't get the right number there. Let's put this back in. Let's try 5 again, make sure I did that right. 5 to the third is 125 minus 20. 125 minus 20 is 105. 105 plus 10 is 115. Right, so I got that right. And then plug in a 2, 8 minus 8, 0 plus 2. All right, so we got it. 5 minus 2. And we have miles per hour per second. 115 minus 10 is 105 over 3 miles per hour per second. All right, I believe that 3 will go into 105 evenly. So 3 will go into 10 3 times, 1 left over, so 35, and my units are miles per hour per second. Okay, for the average acceleration. So this means that every second the velocity increases 35 miles per hour. So this particle gets 35 miles per hour faster every second on average over that time interval. All right, so here's another fun problem for you. I want you to simplify the difference quotient for this function. So pause the video, work that out, and then we'll go over the solution. All right, so hopefully you were successful with that. First of all, what is the difference quotient? Okay, it's a little abstract and you may be having trouble memorizing it. But the good thing is you really don't have to memorize it. Okay, all you have to do is understand what it is and understand that it's really just the average rate of change, and you'll be able to come up with it when you need it without actually trying to memorize it. So let's see if we can come up with what the difference quotient actually is. So suppose that I have just some random arbitrary function. So this is some function f. Here's the point x. And I'm going to move over just a little bit. So whatever this x is, I'm going to add a little number h to it. Just a tiny little number h. So if this is x and I go this direction h, this will be x plus h. So think about it, if this was 3 and my h was maybe 0.1, then this would be 3 plus 0.1 or 3.1. So 3 and 3.1. Right? So if this is x and this function is f, this value would be f of x. Just like if this was 3, this would be f of 3. Right? This is x plus h. So this value would be f of x plus h. So like if this was 3.1, this would be f of 3.1. Right? If I want to find the average rate of change from x to x plus h, remember that I'm just finding the slope of this secant line. You guys all know how to find the slope of a line. y2 minus y1 over x2 minus x1. So the average rate of change would be equal to y2 minus y1, so f of x plus h minus f of x over the change in x, so x plus h minus x. Okay, so the slope of that secant line is the average rate of change of the function, which is this. All right, we can simplify this guy. X plus h minus x, the x's cancel, and you're just left with f of x plus h minus f of x all over h. And this is called the difference quotient. Okay? And maybe you have trouble memorizing this, but again, you don't have to memorize it. Just understand what it is. It's just the average rate of change of a function from x to x plus h. And you can draw this picture, and then you can easily come up with it for yourself. All right, so now let's find the difference quotient as applied to this function. So difference quotient is equal to f of x plus h minus f of x all over h. And I'm going to get rid of all this mess over here now. All right, So here I have this function, and I want to simplify the difference quotient. So first of all, I've got f of x plus h. Remember, if you say f of something, no matter what that something is, you plug that something into the function. So if I do f of x plus h, I want to plug x plus h in for all these x values. So f of x plus h will be, f of x plus h will be 3 times x plus h squared minus x plus h plus pi. So this whole thing here is f of x plus h. All I did was plug x plus h in where I saw the x's. 3 times x plus h squared minus x plus h plus pi. Make sure it's essential that you have these parentheses around the x plus h. You have to subtract the whole entire thing minus all of it. So you have to have these parentheses. All right, so this is f of x plus h. Now I've got minus all of f of x, the whole thing. So if I'm going to subtract this entire function, I've got to have this entire function in parentheses. 3x squared minus x plus pi. Again, it's essential that you have these parentheses. You have to subtract the whole entire thing, all of it, minus the whole function, the whole thing. Got to have it in parentheses. All right, so far I've got f of x plus h minus f of x all over h. All right, now, so this is the difference quotient applied to this function. Now we're going to simplify all this mess. All right, so here, order of operations, I have to do exponents first, so I have to square x plus h. Okay, so I'm going to do this real slowly, make sure we all understand. So if I square x plus h, that's x plus h times x plus h. So I get x squared plus xh. So x squared plus xh plus xh. Plus another xh here, and then plus h squared. So again, there's x squared, x plus h, another x plus h, and then h squared. So I end up with 2 xh's is h squared. So I work this out really slowly. You need to be able to do this in your head. You need to be able to multiply out a binomial, square it, and understand that you get this. All right, so if x plus h squared is that, and then I multiply all of this times 3, I will get 3x squared plus 6xh plus 3h squared. So all of this is just that. Right. Minus, in parentheses, all of this. So it'll be minus x, and then extremely important, it's got to be minus x and minus h. Got to have that minus h right there. Plus pi. This minus has to be distributed to all of these terms. It's got to go with all of them. So minus 3x squared plus x minus pi all over h. All right, now some really cool stuff happens and things start canceling out. So notice I've got 3x squared minus 3x squared. Those cancel. I've got, let's see, I've got minus x plus x. Those cancel. I've got pi minus pi. Those cancel. So now I'll come up here, get rid of our scratch work. Write down really carefully what we've got left. So I've got 6xh plus 3h squared minus h all over h. All right, notice that up here on the top, each term has an h in it. So I'm going to factor an h out of all of that. So that'll leave me with 6x plus 3h. And then a lot of people make a mistake here, so be really careful. If I factor an h out of that, that'll leave me with minus 1. Double check myself. If I multiply this h back, if I distribute it, I would get 6xh 3h squared minus h. So that's right. And it's still all over h. All right. These h's will cancel as long as h is not equal to 0. So my final answer would be 6x plus 3h minus 1, assuming that h is not equal to 0. All right, 2 more problems for your amusement. Again, pause the video, work those out, and then we'll go over the solutions. All right, so I've given you this function, and I want to know if it's even, odd, or neither. So I don't tell you to graph this function, but it's often and usually a good idea to make a graph so you can see what's going on. So let's think about this. You guys know what the absolute value function looks like. If the function was just y equals absolute value of x, the vertex would be at the origin, and it would look like a V shape. So this minus 3 outside of the parentheses or outside of the absolute value will just shift down 3. This multiplication by 2 will just make it skinnier. So my function would just look like this. Okay. And you could plot some points and you would come up with that if you want to just plot points. All right. So is this even, odd, or neither? So you guys know that if it's symmetric around the y-axis, then it's an even function. So clearly, this is symmetric around the y-axis. So this function should be even. And so we think it's even. We need to actually prove that, though. So the test is to plug negative x into the function. Okay. So I'm going to plug negative x in here. So I'll have 2 times the absolute value of negative x minus 3. That's equal to 2. All right, the absolute value of negative x. Now be really careful here. The absolute value of negative x is not x. Okay, so let's think about that a second. All right, so is this a true statement? Is that true? Okay, so let's plug in some numbers. Say that x was equal to 5. Okay, so if x were equal to 5, this would be the absolute value of negative 5. And I said x was 5, so that. Now, is this a true statement? Is the absolute value of negative 5 equal to 5? Yeah, it is. It works. So it's true. But let's do something different. Let's say that x was a negative number. Let's say negative 3. So x is going to be negative 3. So if I put a negative 3 here for x, I'll have a negative 3. So that's a positive 3. Absolute value of 3 is equal to 3, those are not equal to each other. So this is not a true statement. Absolute value of negative x is not equal to x. That's not true. Okay. What is true though? What if I did this? Is that true now? Okay. So now, no matter what I get over here, what I put in for x, I'm always going to get a positive answer. So if I put in a negative 3 for x, then that would be a positive 3. Down through here. And you would see then that it would be true. So that is a true statement. So the absolute value of negative x is the same thing as the absolute value of x. That's 3. Notice that this was just the original function. So that's equal to j of x. Okay, so this is our test or our proof that a function is even. J of negative x is equal to j of x. If you can plug in the opposite of x and get the original function back, then it is even. Okay, so if I plug in the opposite of x and I get the original function back, it's even. If it's symmetric around the y-axis, it's even. Hey, remember, for an odd function, if I plugged in negative x, I should get the opposite of j of x. So j of negative x would be negative j of x for an odd function. And an odd function would be symmetric with respect to the origin. All right, let's have a look at number 11 here. So I've got the point 8, 2 is on a graph of f. And then I've got this new function that involves some transformations to the f function. All right, so I'm going to start with this point that's on the graph of f, and I'm going to move it around according to these transformations. So first of all, I got x plus 1 inside the parentheses. So that means I'm going to shift this point 1 unit to the left. Okay, so now I'm going to be over here. So this point will now be at 7, 2. I'm going to multiply that f value by negative 3. So that means I'm going to multiply the y value by negative 3. So now I'll be at 7, negative 6. So I just multiply the 2 times negative 3. Right. Then I'm going to add 20 to the g of x value. So if I add 20 to my y, 20 plus negative 6 is 14. So I'll be up here at 7, 14. Okay, so 7, 14 would be a point on g of x. So that would be the answer. 7, 14. All right, let's double check that and make sure it really works. So I'm claiming that if I plug 7 in for x in the g function will spit out a 14. Let's make sure that that's really true. All right, so g of 7, and this better come out to be 14. G of 7 is equal to negative 3 times f of 7 plus 1 plus 20. So that's negative 3 times f of 7 plus 1 is 8 plus 20. I got negative 3 times, what's f of 8? Well, since 8, 2 is a point on the graph of f, then f of 8 has to be 2. That's a 2 plus 20. Negative 3 times 2 is negative 6. I got negative 6 plus 20, which is 14. So g of 7 is 14. So 7, 14 is a point on the graph of g. All right, 2 more problems for your entertainment. So pause the video, work these out, and then we'll go over the solutions. All right, so on the first one, I've got f of a is equal to b, and g of a is equal to c. I want to know what f minus g of a is equal to. All right, so by definition, f minus g of a is equal to f of a minus g of a. Okay, so that's just the definition of what this new function means. F of A, I told you, was B. G of A, I told you, was C. So there's the answer, B minus C. So it's just that easy. Make sure you understand graphically what's going on here. So I've got some function F, and I know that if I plug in A, I get B out of it. So I know I get this point. I don't know what F looks like. Maybe it looks like that. There's our function F. I've got another function G that if I plug in A, I'll get C. So maybe it looks like this. We don't know that. All we know is this one point. So then if I do F of A, which is B, minus G of A, which is C, I'm going to get another point down here for my G function, which is B minus C. So maybe it's down here somewhere. Okay, so here's my point, B minus C. And I don't know what the G function would look like. It would probably be something about like that. But I know that if I plug A into this G function, I'll get B minus C. All right. Over here, I've got two functions, 2 to the x and the square root of x. All right, I want to know F of G of 9. So this would be F of G of 9 means I plug 9 into the G function. So G of 9 is equal to the square root of 9, which is 3. So now I want F of 3. So I'm going to plug 3 into that F function. Get 2 to the third, which is 8. So notice what happened here. I took the x value of 9, I fed it into the G function. G spit something out, and whatever it spit out, I fed into the F function. So 9 went into G, G spit something out, whatever it spits out, I feed into the F. So I plug a 9 into the G, and it spit out a 3. Plug the 3 into the F, and that spit out an 8. All right. G circle F of x. Remember, this is just a symbol that means G of F of x. That's just what that means. So I'm going to plug F of x, the entire function, the whole thing, into the G function. G of that. So that would be G of 2 to the x. So I'm going to plug 2 to the x into the G function. So if I do that, I'll get the square root of 2 to the x. All right, let's have another look at this problem number 12 here. Even though the answer we got is exactly right, and this really has nothing to do with the answer, this graph I drew we need to look at this a little bit more. So here we had F of A was equal to B and G of A was equal to C. The way I drew this graph, which again is just completely arbitrary, I just made it up. C is a bigger number than B. So if G of A was equal to B minus C, then I'm subtracting a bigger number from a smaller number, which would mean that G of A needs to be a negative number. So this graph wouldn't be right the way I drew it. And again, that has no bearing on the answer to the problem. It just bothers me that I didn't really draw that correctly. All right, so since G of A is C, F of A is B, and the way I drew this, C is bigger than B. When I do B minus C, I should get a negative number. So G of A needs to be something below the x-axis. It needs to be down here. And notice numbers out here, these values are getting bigger, and these values are getting smaller. So if I did b minus c, where these are getting smaller and these are getting bigger, then the values of g should be getting smaller and smaller all the time. So g needs to look something like that, and probably the same way over here, needs to look something like that. So just to clarify the completely arbitrary graph that I drew, I need to make that more realistic. All right, here's another interesting practice problem. Pause the video, work this out, and then we'll go over the solution. All right, so here's our function, 1/2 x squared plus 3. We want to write an equation for the inverse of that. So again, inverse just means, or the inverse relation just means to switch the x and the y's. So I have y equals 1/2 x squared plus 3. So this is y. I'm going to make that the x and make that the y. And then I'm going to solve this equation for y. So I'm going to subtract 3 from both sides. 1/2 y squared. Okay. To get rid of the 1/2, I'm going to multiply both sides by 2. So I'll have 2 times x minus 3 is equal to y squared. Take the square root of both sides. Remember, I will get two solutions, so plus or minus the square root of 2 times x minus 3. Okay, so the first thing to notice is this is not a function, because if I plug in an x, I'll get out two different values for my y. So this will not be a function. And of course, this is not one-to-one, because it's a parabola. So since this is not one-to-one, its inverse can't be a function. All right, so let's graph f and its inverse. So first we graph f. This is just a parabola. A couple of transformations to make. The plus 3 will shift the original y equals x squared parabola up 3. Okay, so I'll come up here to 3. The 1/2 will just make it fatter. Okay, so I'll have a parabola. That'll look something like that. Okay, since I'm graphing f and its inverse, the line y equals x is important, so let's put that in. So there's the line y equals x. And just to make sure this all is working good, let's put in a point or two and see what happens. So if I put in a 1 for my x value, or let's do 2 actually. So if I put in 2 for my x value, 2 squared is 4, half of 4 is 2, 2 plus 3 is 5. So I would get the point 2, 5. Of course, the same thing for negative 2. If I plugged in negative 2 squared is 4, half of 4 is 2, 2 plus 3 is 5, and I would get the point negative 2, 5. And of course, 2, 5 is above the line y equals x, so we're good there. If we put in, say, 4, 4 squared is 16, half of 16 is 8, 8 plus 3 is 11. So I would have the point 4, 11. And of course, I would have the point negative 4, 11, because that's an even function, symmetric around the y-axis. All right, I want to graph the inverse, so all I have to do is switch all these x and y values. So here is 3, 0, so I would need 0, 3. There. I have the point 2, 5, so I would need the point 5, 2, which would be, since that's 3, there's the point 5, 2. I've got the point negative 2, 5, so I would need the point 5, negative 2. Should be about there. I've got the point 4, 11, so I would need the point 11, 4. I've got the point negative 4, 11, so I would need the point 11, negative 4. Is there. And you see that we get this parabola turned sideways. Notice it has been reflected across the line y equals x. All right, here are the last two practice problems we'll do. I would suggest doing number 16 first. So do this one first, and then go back and do 15. Pause the video, work those out, and then we'll go over the solutions. All right, so the first one, if AB is a point on the graph of F, then what's a point on the graph of F inverse? All right, so this is extremely easy as long as you know what the definition of F inverse means. So you guys know all you have to do to find the inverse is switch the X and Y. So this is extremely easy. A point on the graph of F inverse would just be B. By definition, what F inverse means. Make sure, again, that we understand that graphically. So here's the line y equals x. So if the point, let's say A, B, say that's a point on the graph of F, then F inverse, so here's the point A, B. We know F inverse is going to have the point B, A. And then the graph of it would just be a reflection of that. Notice that it is reflected across the y equals x line. All right, let's look at the final question here. So H, circle H inverse of pi. Remember, by definition, this means H of H inverse of pi. Okay, so we're going to plug pi into H inverse. That's going to spit out a number. Whatever it spits out, we're going to plug it to H. Okay, so let's think about that graphically. Okay, so here I've drawn the line y equals x. All right, so if I plug pi into H inverse, it's going to spit out some number. We have no idea what it is. But let's say we get this point. So we plug in a pi, and it spits out something, question mark. Okay, so this is the point, pi, question mark. And this is H inverse here, so I'm just going to draw some random function. So here's H inverse. I plug in pi to H inverse, it spits out question mark. What's the inverse of H inverse? Well, that would be the original function, H. So what would be a point on that? So a point would be question mark pi. So there's my H function. So if question mark pi is on H, then pi question mark is on H inverse. All right, so now let's think about this. So I plug pi into H inverse and I get something. I get question mark. So H question mark. What's H of question mark? Well, H of question mark is just pi. So H, circle H inverse of pi, is equal to pi. Right, so if you compose two inverse functions like this, whatever you plug in, you'll get the exact same thing back out. Let's do this the other way around just for fun. This wasn't part of the question, but it's interesting. Let's do H inverse, circle H of pi. See what we get. So again, this means H of, it means H inverse of H of pi. Right. So that'll be H inverse. Now, what's H of pi? Well, I don't know what H of pi is. I don't tell me over here. So let's just pretend. So let's start over here. Let's pretend that we plug in pi to H. We'll get some point. Let's say that we get out star. Okay, so we plug in pi and we get out star. So this point is pi star. And this function is function H. If pi star is on H, then star pi is on H inverse. And that is clearly not what H inverse would look like. Let's just draw the point, don't worry about the graph. So if pi star is on H, then star pi is on H inverse. So now let's answer this question. What's H of pi? H of pi is star. H inverse of star is pi. So again, we've composed the functions, H inverse and H, just in the opposite order we did up here. We plugged in pi and we got pi, we plugged in pi and we got pi. So make sure you think about that and make sure it makes sense. This is very important. If you compose two inverse functions in either order, every number you plug in, the same number will be spit back out of the composition.